And this is our last session for our workshop. And we have 3 talks and then a session for some discussion. Okay, so let's start with a talk by Lawrence on typed, concise, and Nanopass compilers.
Thank you. So this talk is about, can you guys hear this? Okay. This talk is about writing maintainable compilers in Agda. And well, there are several things you'd want from a maintainable compiler. So you probably want it to be typed. You probably want it to be concise, so not much source code for there to be bugs in. And you probably want it to be modular, so you have separation of concerns and so on. And you probably want to have all 3 of them at once. And well, the purpose of this talk is to show you how to do it. And to keep this talk accessible, we're going to build it up from first principles. And since we're at TyDe, first principles, well, that's got to be the types. Up a little bit. Is that better? Ah, thank you. Hopefully I'm louder now. Right, so we define the types of our expressions. So this is fairly standard. It's a language of literals, addition, lambdas, application, variables, let bindings, and so on. Oh, that's very loud. The important thing here is we've got some constructors and they all return its expression. And what then a compiler is just a function from expressions to expressions. And we can use it using develop it using the standard techniques of hole-driven development. Well, we put a hole in, we use some key bindings and to tell Agda how to develop the function for us. And we can start filling in these holes. So some of them are easy, some of them you need to write a little bit more depending on what your compiler is going to do. So we want to convert lets to wheres in this compiler, among other things. And you fill it in and you refactor it and you can press it. And maybe at some point you need to realize your compiler needs to be monadic. So we add a monad on the output and we keep programming and refactoring and hack on the compiler until it eventually becomes like this. Now, is this a maintainable compiler? Let's have a look. Well, it's typed. You can't produce ill-formed programs. It's concise. There's no bloat code here. Every line is doing something. But it's not really modular. And well, we can see it's not modular. If we wanted to remove one of the features of this compiler, say we wanted to remove the lambda lifting, well, you'd have to remove those lines, but you'd also have to look at every single other line to see if it's not somehow contributing to the lambda lifting. So actually, you've got to read every single line of code in this compiler every time you make a change. So well, it's not modular. So we've written a compiler that is typed and concise, but not modular, and well, I'm going to call this a monolith. Let's try and get to the goal and, well, improve on modularity. So we go and read some papers, and well, this is a famous paper about compiler architecture, and it tells us that we should structure a compiler as a collection of many small passes. So we can do that. Our compiler is now many small passes, and a single pass looks something like this. So this is the where to let conversion pass, and well, the first line's doing the action, it converts where to let, but there's this other stuff too. So a lam converts to a lam, and then we recurse. An application node, well, that's an application node as well, and we recurse. And well, addition goes to addition, and so on, and everything else goes to everything else. How's this maintainable? Well, it's modular. I don't see this pass doing anything other than where to let conversion. It's typed, it's not producing ill-formed programs or accepting them, but it's not concise. Why do I say this? Well, if we look at it, most of the code is boilerplate. How much boilerplate? Well, we've got O of k boilerplate here, if k is the number of constructors in your data type, but that's not all, because we've got a nanopass and we've got many passes. So if each pass is like this, we've got, well, O of n passes, so in total we've got O of n times k boilerplate. And if we take nanopass at the extreme and we have about as many passes as we have constructors, this is quadratic. So that's not concise. So the story so far is we've traded, well, conciseness for modularity. So well, let's try and get back the conciseness without giving up modularity. Let's have a closer look at our compiler. This boilerplate code, it's doing a traversal. So, well, wouldn't it be nice if we could replace all this repetitive traversal code with just a single line that did it all? And well, like a map. And if we did that, hopefully it would solve our boilerplate problem. We just need to implement this map function. Well, the type of map is this, and well, we want to use it in our definition of the program syntax. We can do it like this. So we define our program syntax as a tree, a rows tree, so arbitrary branching factor. But of course, it's got to have some payload as well. And what the payload is going to be carried in this type, call it head, for the head of an expression. And we can define this fairly mechanically. So we start off with our old expression type. We strip out all the recursive parts, because these are now covered by this args field, which stores the recursive parts in a list. And well, that gives us the head. We rename it and tidy up. And let's have a look at what a pass looks like next. It's still a multi-pass compiler. And a pass looks like this. So notice how we're using the list now to extract the sub-expressions and build them up. Is this maintainable? Let's see. It's concise. It hasn't got any longer. In fact, it got substantially shorter. It's still modular. It's not mixing up functionality that should be in other passes. But it's not typed. So we have a look at it, and well, on the second line I wrote EB, but well, maybe I should have written BE instead. The type system's not giving us any hints here. And maybe we shouldn't have used a singleton list. You know, maybe we should have taken account of the fact that there could have been other children, or maybe that doesn't make sense and we do just want the singleton list. So in short, this compiler is a complete bug fest. And well, yes, users can put in complete garbage programs. So this program claims to be a single literal, but it has children, so that doesn't really make sense. So far what we've done is we saw a monolithic compiler, and then we upgraded it to a Nanopass compiler at the cost of some extra boilerplate, and then we got rid of the boilerplate, but this cost us our type safety again. So let's try and get some type safety back. If we look at our compiler and syntax again, well, I'm going to pin the blame for lack of type safety on the list function, on the list type, because it's these pattern matching on lists that are overly permissive. And well, we don't use lists for anything else really, so we could replace it with a custom data type, call it args. Provided we also replace all the occurrences of lists, so the map function, and we replace these pattern matches on list with pattern matches on our new args type. And we can craft this args type such that we only have these specific pattern matches in it that correspond to well-formed programs. And well, we probably want to rule out programs like this as well, where you shouldn't be able to have the arguments for a where expression applied to a literal. And to do this, well, we can add an extra index to the args type so that only the args for a specific type of head are allowed. So this would not pass type checking. How do we design this args type? Well, again, we start with our expression type. We strip out all the bits that are all the bits that are not recursive, because those are taken care of by this head type. And well, we put in the bits that are supposed to be parametric, and we compress, and we rename, and we remember that we need to put in this index, and we fill it in the obvious way, and we're done, right? Except that the edge of the slide is hiding a pretty big problem, and that is that that some of these heads take an argument. But we can bulldoze our way through this problem by just, well, taking an argument in the constructor as well. And then we realize that, oh, well, the head is just duplicating the data. So actually we can take the payload out of the head and put it back in the args type. So this is basically our expression type again now, but indexed. And we refactor it, and compress it. And well, at this point, head is just a tag, so well, we can fit it on one slide and rename it. Oh, and well, since it's not doing much anymore, we'll just make it implicit for now and have a look at our compiler pass again. So now a single pass of our compiler looks like this. Well, it's still got type X to X, but it looks quite a lot like the list-based compiler, but instead of pattern matching on lists, it's pattern matching on this args type. And we've preserved the property of the list-based compiler where the boilerplate uninteresting cases are implemented via map rather than listing them out individually. Let's see how we're doing for maintainability. It's typed, that was the whole purpose of this refactoring. It's concise, it didn't get any longer. And it's modular as well, right? So it seems we're done. We've designed a typed, concise, and modular compiler, right? Seems a bit too good to be true, and it is. So let's have a look at our compiler again, and well, it's concise, typed, and modular, but what about the proofs about our compiler? So well, let's say we implement the inverse of this compiler pass. So the top one is converting where to let, and the bottom one is, well, it's converting let to where. And let's try and prove that they're inverses. And actually, they aren't inverses because, well, the wheres disappear. So, well, we've got a kind of idempotence property. It's almost an inverse. And, well, the proof, it looks like this. So that's not concise. So actually, we're back in the same corner as we were with the conventional Nanopass compiler, which is typed and modular, but not concise. So let's see how to fix this. So the root cause of the problem is we write a code like this. So this is another pass. It's a pass that scans through your program source code and looks for calls to error. And you write this, but actually expands it to something like this under the hood. So you write a catch-all case, but Agda treats it a lot like if it listed out every case explicitly and had the duplicated right-hand side. So when you go to prove properties about the function, you actually have to treat every case individually and, well, case split, and, well, your proofs become verbose, even if your pass was not. And, well, it's a big split because the type we're splitting on has many cases. So perhaps we can fix this by splitting on a simpler type. And, well, you might think, well, let's split on head, that's simpler. But no, it's not, because head has exactly the same number of cases as arg h does for unknown h. So let's try and make it even simpler and split on a type with size 2, and that will mean that at most 2 cases, and we shouldn't have these big splits anymore. Like maybe. How can we get a maybe? Well, we've got these heads exposed, so we can get a maybe by just testing them for equality. And this code actually works, but it's a bit ugly. We've got an extra line, and it seems that every time we would be making a case split, now we've got to write this with in front. So let's do something about it and postpone the problem. So instead of having with in our compiler pass, now the with is done beforehand, and the result is passed in as an argument. And, well, this gets us closer to the style we used to have. But, well, the types get uglier. And, well, to make the types get shorter again, we can observe that we've got this expression type. How about we put the second argument, this maybe, into the expression type, and we can do that, but we don't want to hard code it, so we dig out a parameter for that, and then, well, we move this second argument into a parameter of the expression type, at which point we don't need the dependent type again, and it all fits on one slide. And well, we can save a few characters as well to make the rest of the program fit on the slide. So we rename the constructor, we switch maybe out for either and an unknown parameter. And it's pretty concise now. Let's see how this works for our where to let and let to where functions. So here they are. Here's where to let and here's let to where. They look similar to before, but the X type's now got this parameter, and we're passing around this this proof that the current head satisfies the predicate being passed around in the type. And we can write the round trip property. And the proof is now constant length. It's slightly more complicated because in the second case we need to use both of the functor laws for when we map over the args type, but it doesn't grow as we increase the number of constructors or the number of passes. So looking at if it's maintainable, well, the compiler passes are just as maintainable as they used to be, and the proofs are also, well, typed, concise, and modular. So this time we actually have hit the bullseye, and we've got a typed, a concise, and a modular compiler. And, well, we're getting to the end of the talk now. So we've got a typed, a concise, and a modular compiler. The definition of the language's syntax is the star of the show. We achieve, well, O of k plus m total amount of code, where k is the number of constructors and m is the number of passes. Although you should be a bit skeptical of this, because there are some quite big constant factors hidden by the O, and well, they're hidden in the glue code between the individual passes. But it's a constant factor. You should also be skeptical of the fact that I've kind of conflated modularity with Nanopass architecture here, and well, there might be other ways to get your compiler to be modular, depending, and well, have the proofs be modular as well, depending on what properties you like. And well, this is work in progress, and it's time for questions.
Questions?
Hi, I was wondering, like, what's the biggest compiler you've written in this system?
Ooh, pretty much the one I had on the slides. So this one, it does lambda lifting, where to let, it logs the errors, it evaluates top-level constant arithmetic as well. So not a real scale compiler.
Right, and then each one of those features is a different Nanopass?
Yes.
And then sort of what's the glue to put it all together?
I can show you. So it's mostly these weakening passes to change the type of the parameter. I'll open this up. Oh, okay. Sorry, I can't find it on my disk in a reasonable time, so.
No worries, yeah. You can show me later.
Yeah.
I have a question about tagless finals. I think your approach is quite similar to tagless final, except in tagless final it never considered about proofs, and you also consider about the conciseness of proofs. Do you think there are other differences between the tagless final approach and your approach. Are you familiar with the tagless final
No, I'm
approach?
not familiar with tagless final.
So it's something on Oleg's web pages. So in that case, you usually define like a base case that you include, and then you define just one constructor that you modify. So there are some similarities between your approach and their approach. Maybe I can send you a link afterwards.
Oh, yes, please.
And I was wondering also, have you considered about testing the compiler? So you've got 3 dimensions already, right? You've got the way you write your Nanopass. You've got the proofs. So how would you test the compiler for? Is the proof essentially the test for the compiler, or do you need more than just the proof for testing the compiler?
Depends on what you prove, I guess. I don't see why this would be particularly hard to test. You can instantiate the p parameter to be whatever you like to help with testing, and then make up some test inputs and test outputs and run it and see if it's equal. So I don't see how this particularly helps or particularly gets in the way of writing tests.
Yeah, I think it's nice for testing as well. Okay, thanks.
Hi, I saw that you were using Agda, and I wondered why, if you've considered actually typing your expressions in a way that the types actually appear so that you know that all your transformations are type correct, and whether or not that's too hard to work with, and also sort of why Agda?
So for whether or not to put types in the program, I didn't do it here because I think it's sort of orthogonal and it would be a bit of a distraction from the technique. I think it should work. The main obstacle I see though is, well, we have this. We put all the intermediate representations into one args type. So if you want to have substantially different intermediate representations, and in particular if you want to have different indexes on the types of rows, and you want to change the type systems effectively for your intermediate representations, then that would get harder, I think.
I see. Thank you.
Let's thank our speaker again.